You're looking at a computer representation of a violent thunderstorm in Homedale, New Jersey, which occurred in July of 1966. The rain is heaviest on all white squares. In a little while, many squares in the lower right corner will be white or nearly white, indicating that the heaviest rain is there. My name is Anne Freeney, and my colleague John Gabby and I made this film at Bell Laboratories in 1968. Our objective was to find lengths of rain rate data which might be candidates for modeling the intensity and movement of heavy rainstorms in over 400 hours of recorded rainfall. The data came from a network of rain gauges installed in a 50 square mile area in central New Jersey. Whenever it rained in 1966 and 1967, this network of gauges automatically recorded a rain rate measurement every 10 seconds. The 96 gauges were approximately 8/10 of a mile apart in an irregular 11 by 10 grid. In this film, the measurement from each gauge is transformed into a shading for a square which represents the area in which the gauge is situated. The grid is oriented so that the top of the picture is north. Light rain is shown as gray. The heaviest rain rates, as much as 200 millimeters per hour, are shown as white squares. The lightest rain rates appear as half gray, half black. Occasionally, a square that was shaded turns black for a while. That means that the gauge associated with that area temporarily stopped transmitting data. The movement of the white squares to the lower right corner since the film began indicates that the most intense part of the storm moved over the grid in a southeasterly direction since the storm began. As we continue to watch the film, we will also be able to tell that the storm has become less intense over the area covered by the rain gauge network, since there will be fewer white or nearly white squares. At the time that this film was made, computer shading techniques were very crude and expensive, and we were trying to achieve a shading that would allow us to see the behavior of rainstorms without using a lot of computer time. We did this by varying the frequency of plotted characters with 2 intensities on a dark background to simulate a grayscale. If you focus on one square of the grid, you'll see that within that square there is an 8 by 8 array of points. A character is plotted at 16, 32, 48, or all of the 64 points. We hoped to find a way of choosing the character intensity and the plotting points so that an apparent increase in the lightness of the square would represent a corresponding increase in rain rate. Incidentally, the distracting flash of white in the upper left corner of certain squares from time to time was caused by an error in the graphics software. We also had to choose the number of times each 10-second scan of the network of gauges would be repeated on the film in a way that would speed up the rainfall over real time, but not so much that changes would occur too fast to see. In this segment of film, we are seeing about 20 minutes of rainfall in a little more than 4 minutes. Because our goal was to pick out interesting data rather than to use the film as a data display technique, we did not do either spatial or temporal smoothing. As you might be thinking now, this way of showing the rain rate data wasn't very successful. Rain rate turned out to be extremely variable in both space and time, and movies emphasized that variability so much that patterns of movement of heavy rain were very hard to detect by eye. A static display of the data as a 2-dimensional set of time series, which we won't show here, was a much more useful guide to finding interesting pieces of the data.